focus on just finding particular solutions. General solutions, then just complementary plus the particular. We're doing variation parameters, right? So the first thing we have to do is form the fundamental matrix, which is finding a complementary solution. And just wind up using Wolfram to do all of the work for me. Eigenvalue to the command, then you need to enter a matrix. So this is going to find all the eigenvalues of the inputted matrix. Remember, for a matrix, the entire matrix itself is around braces. Each row is within its own set of braces. So there are two eigenvalues, 1/2 and 3/2. It's probably also I'll put them in table form, so it lists it out as a column instead. Doesn't matter. Fundamental matrix. Let's call it M. Oh yeah, I'm not going to do that yet. That's right, we have to actually, unfortunately. Find the eigenvectors first. I'm going to define A of X. A minus lambda I, or xi. I'm going to do two things. Row reduce the matrix for 1/2, or reduce the matrix for 3/2. This will now allow me to form the fundamental matrix. One-half e to the t over 2, right? Times eigenvector. That's the first column. Second column, e to the 3t over 2 times eigenvector. First eigenvector 2, 1. Second eigenvector, 10, 3. And what I'll do is that would be your fundamental matrix. Now we're going to go ahead and form a particular solution, doing all that fun stuff. I'm not going to worry about showing everything, right? I'm not going to have it print out what the inverse is, what the products are. I'm going to do it all in one go. All right, the fundamental matrix times the integral inverse of the fundamental matrix times if times your f of t which was e to the t over 2 negative e to the t over 2. that. Close that out. Let's put that in matrix form. There's your particular solution. So again, I'll just take these on the slides. And I'm not going to go any further than that. I'm going to say, yep, there's the particular solution. That's all I want. So what I'm going to do here, let's go ahead and define the coefficient matrix, which was 1, 8, 1, -1. Define a of x, a minus x times 2 by 2 identity. So we're going to define f of t. Which is that vector. I can't define my n yet. I can't find the eigenvalues. Eigenvalues -3 and +3. Just plug those into A or reduce. Use those two matrices. What is one solution?
-2
Times what?
e to the -3t.
That's one solution. What's the second solution? Or what? Times what?
4 times 1.
Times what? 4, 1 times what?
The exponent of -15.
Not -3.
Oh yeah, that one's positive.
There's our fundamental. I forgot to simplify. Yeah. And matrix form. That. They must have updated Wolfram since I last ran this. This didn't give me. Oh, I don't care about there. Didn't give me the hyperbolic function the last time I ran this. Now, granted, this was several years ago. I can fix that. If you don't want the hyperbolic function, cool, it actually now lets me recall other things. That is a new feature as well. Output 17, trig 2 exponential. We have to re-put it into matrix form. Oh, maybe it's because I did simplify, not full simplify in here. That might be it. Let me test that. That was there, that's why. Full simplify getting the hyperbolic, just regular old simplify. We'll keep exponential. And that would be your particular using variation of parameters. I challenge you, of course, to do all this by hand. And then appreciate the computer. What I'm going to do is this. think I promised to do this on the calculator too, didn't I? So the next one's gonna be perfect for that then. Obviously, it's not gonna be as nice as Wolfram. Here's the next one. Start off saying we're going to define the coefficient matrix. Guys, remember there's two ways to do it on the calculator. Menu, where are you? Matrix and vector, create, matrix, and then you just have to enter number of rows and columns. Okay, and it does it for you. Now just put in your components. Enter, that's now stored. Alternatively, it's just this. In your brackets, first row, all elements of that row separated by commas, semicolon separates your rows. If I just hit enter here, that'll give you the matrix. So whichever way you want to do it. We have our A. I'm also going to define my f of t. The calculator does not differentiate between capital and lowercase. So capital F, it will still read as lowercase f. Which is why I'm not using capitals, so there's no point. Let's define that. Secant t, comma, or not comma, sorry, semicolon, 0. There's your trig button. All your trig functions as well as the inverse functions. Instead of having to type it in. Ah, cool. If you keep on hitting it, I know that. It scrolls through them all. And then you just hit enter when you're on the one you want. I did not know that. I always use the mouse feature. The arrows, that's nice. Is there anything else I needed to define? Oh yeah, for web reducing. I can't use capital A because it's going to read it as lowercase a, so I'll just use E for eigenvectors. A minus x times that, but I'm not going to risk that. Let's go up to menu, vector, create, identity matrix. That is just identity. Okay. 2. Now what was it? It was I. Menu, matrix, and vectors. I know it's down.
Advance.
So next, eigenvalues. Oh, BIG capital DL, okay. We want the eigenvalues of A, right? Uh-oh. Oh, dear. Settings. Make it rectangular. Excellent, rectangular. I negative I. That's nice. Now we just row reduce, right? So REF or menu, matrix, and then row reduced echelon form number 5. We wanted E of I. So you can't just type in I. We actually have to go look for it. If I'm not mistaken, it should be right here under the pi. Yep, there it is. Pi. Let's go look at pi. This I'm probably gonna have to write stuff out on. That gives us this eigenvalue, right? Or this eigenvector, right? We use a capital lambda to represent the eigenvector. I1, right? Which can be split to 0, 1 plus 1, 0 all times I. Remember the purpose of doing that. The real component's B1, the imaginary component is B2.
Could you switch the screen so we could see?
Did he yet? Oh, goodness, I thought I did. Let's switch that. I'm also going to put down this. Up there, the eigenvalues. All right, alpha 0, beta is 1. Because remember, your two solutions in this case first one, e to the alpha t times cosine of beta t, all times b1, minus e to the alpha t sine beta t, all times b2. 2. X2 what's that? No, that should be D1. Those are your two independent solutions. All right, well, in this case, our alpha is 0, our beta is 1, right? B1 was what? 0, 1? Those are your two solutions. Which we're going to have to rewrite. Now your fundamental matrix is just a matrix where column 1 is x1, column 2 is x2. So let's go ahead and get that in. Do I want to use n? Yeah, I guess I can. So m of t, define that. Do it this way. Negative sine t, comma cosine t, right? That was the first row. Second row, cosine t, sine t. Now with the calculator, I am 99% sure that if I just do a matrix, regular times a matrix, it reads that as matrix multiplication. So I'm just going to try that. M of t times 1 integral, menu, calculus, 3, leave those blanks, we don't want definite, we want an antiderivative. Now we need the inverse, and I'm, again, pretty certain. No, it's not inverse. Oh, bummer. Right, so let's go menu, matrix. Try something. Yes, that is the correct inverse. Notice it didn't change. So that's what it is. So it's going to be m of t times inverse times f of t with respect to t. There's your particular solution. And so that's how you do it in your calculator. It's very similar to what we did in Wolfram, right? Just as a calculator, so it's not going to be written out as neatly. Are there questions on inputting it into either Wolfram or the calculator? Keep that in here. That one. The process is identical for a 3x3 system, except it's now 3x3. And I'm not going to worry about that. And so again, here's I'll give you extra time to work on the worksheet. Okay, so we're done with systems. The last thing we have to look at is the Laplace transform. A little bit of motivation for the Laplace transform. of the forcing functions we've been looking at have been continuous. Well, what if your forcing function is piecewise continuous? The methods that we've gone over does not work. Right, we also have what's called impulses. Right, you can have an impulse force, driving force. The techniques we've covered so far also do not cover that. This is where the Laplace transform comes in. With the Laplace transform, we can now solve those types of problems. Now, the only downside is Laplace transforms can only be used on initial value problems, not to find a general solution. Now that's fine, because in most applications, you're solving initial value problems, right? You don't care about general solutions. So we first define what the Laplace transform is. That's step one. Step two, we look at the inverse Laplace transform. So that's a separate lesson. Then we'll move on to solving them. And I will split it into 2 days, 2 meetings. One will cover, I think I have 8.3 and 8.6. And another day will cover 8.4 and 8.5. And then that's it. That's all that's left for the semester. There's your definition of the Laplace transform. So you want to find the Laplace transform of a function f of t. It's big F of s, which is the integral from 0 to infinity, e to the negative st times f of t dt. Now let's test your knowledge. What's that integral called? What type of integral is that? Calculate.
Sorry, you should repeat. Yeah, I don't know.
You can make up to, this was very simple.
I don't. I felt bad.
Very, very, very sad. It's a type 1 improper integral. Your interval of integration is infinite. That's type 1. Type 2 would be if your integrand is discontinuous somewhere along the interval. Right? And then, of course, we have methods for evaluating each of those. Laplace transform is linear. So Laplace transform of a sum is the sum of the Laplace transforms. And if you take the Laplace transform of a constant multiple of a function, it's just a constant multiple of the Laplace transform. We also have the first shifting theorem, or the first translation theorem, which states if big F of s is the Laplace transform of f of t, then the Laplace transform of e to the at times f of t is just big F of s minus a. Once we get out of the inverse Laplace transforms, I'll provide a table of common Laplace transforms with inverse Laplace transforms, so you don't have to worry about the integral every time. But for today, we don't have that table. So we'll have to do the integral. Laplace transform of 1. Well, that's a fairly simple one. two ways of writing the Laplace transform. When using math typesetting, like LaTeX, that's the script L. Different languages have that as your script L. So you'll see either one. When I'm handwriting, I tend to use the curly version because it's easier. But they just mean the same thing. Laplace transform of 1, using the definition, integral from 0 to infinity, e to the negative st times 1 dt. Now, technically what we would need to do is write this. Do the integral from 0 to r, and then pass that through a limit as r goes to infinity. Yeah. We're in differential equations now. I'm not going to be writing that. That is an understood limit. Especially in physics, we never write the limit. If there's something evaluated at infinity, it is always implied to be a limit, an infinite limit, or limit at infinity, rather. So that's the notion that I'm going to be using. And I'm pretty sure the textbook also does that. What is the antiderivative of e to the negative st with respect to t? That's true.
Oh, do this over two. Oh, never mind. It's negative.
Yes. Because remember, we're treating s as a constant for the same time. And that's going to be evaluated t equals 0 to infinity. Negative 1 over s e to the minus infinity plus 1 over s e to the 0. What's e to the 0?
One.
1. What's e to the minus infinity? Remember, that's an implied limit. So that would be the limit as x approaches infinity of e to the negative x.
Zero.
It's 0. There's your Laplace transform of 1 over s. Let's see if that's actually going to take it again. So that's one of the Laplace transforms that's provided on the table. In fact, just about every one that we're going to be doing today, actually I think all the ones we're doing today, with maybe the exception of one of them, is on the table, so we're essentially driving the table. There will be a few on the table that we don't do in class. T. This one is not on there, but t to the n will be on there. But I'm not doing t to the n. So that's pain. So it's like I'm going to cap it. You get to do it for homework then. You'll see why it's a pain. Right, by definition, integral from 0 to infinity, e to the negative s times t dt. I'm just going to rewrite that in a more traditional order. How would you evaluate that? So you want to find an antiderivative. What's the technique you need to use? Integration by parts. Here's why t to the n would be a pain in the ass. Then you have integration by parts multiple times. Nope. It's always e to the negative st times your function. That's why I'm not doing t to the n.
Would a calculator be able to solve it?
Yes. But I'm avoiding calculators for this lesson. I want to kind of get a feel of what the Laplace transform is doing first. Well, I'm not going to use integration by parts because I gave you an integration table. And t e to the at is on that integration table. It's number 42. One over a squared, so I'll just write out what the formula is. Plus a c, but not c. A is negative s, right? U is t. 1 over s squared times negative st minus 1 e to the negative st. T is 0 to infinity. In fact, you should have done a problem like this in Calc 2, which is why I'm not doing it. E to the 0 is 1. So that second term is just positive 1 over s squared. Right? It's technically negative, it's minus negative. What about that first term? It's 0. Okay, I'm getting annoying. The plus transform of t is 1 over s squared. I will also bring up notation. Your book uses this notation. To represent transforms. That is not the notation that I grew up with. This arrow here is a mapping, and the Laplace transform is just a map. It maps a function to a u function. So I'll be using that vertical bar arrow, but keep in mind your book uses the double arrow. E to the AT. This one would be fun. Actually, I don't think this one's actually that bad. Integral 0 to infinity, e to the negative st times e to the at. A is a constant. Well, can't you write that as this? Which is the same as this. Don't need to redo any of the work. Replace s minus a with just s, and we already did it. So you're 1 over s minus a.
Can you repeat that?
I already did that integral. E to the negative st. We said it was 1 over s, right?
Oh, so since A can be any constant.
Because s is a constant in that case, and for this integral, s minus a is constant. Sine and cosine. Oh boy. This would also be integration by parts, right? Except you have to do it twice and then algebraically solve. Again, you should have done this in Calc 2. I'm jumping right to the table. This is number 44. Oh, God, I'm not gonna frame it. I'm ignoring constant integration on the ship. A is S, or negative S rather, and B is omega. So let's look at that second case first. E to the 0 is 1, right? What's sine of 0? What's cosine of 0? That just becomes omega over s squared plus omega squared, right? Again, negative but minus negative. So now what about that first term? It's 0. Both sine and cosine oscillate, but it doesn't matter. Because that's all being multiplied by E. E is shrinking to 0. So yeah. Well, that may be oscillating, multiplying by something that's shrinking to 0. The whole thing shrinks to 0. Left with omega over s squared plus omega squared. Good. Set up the integral. What's the integral for this Laplace transform?
integral 0 to infinity e to the negative st times cosine omega t dt.
We have 23 minutes. For 2 points extra credit, you back that into all your groups. With no table, do it all by hand, using the original parts. Towards the end, I'll have you turn it in, I'll start the recording again, and write out what that evaluates to. All right, let's turn it in.
You would end up, as long as you have the
Your name's on it?
Oh, yeah. As long as you have the exponential and the trig. Yeah, you're still left with an exponential and trig functions. So you would end up.
Okay.
That's why I'm confused.
So get your names on, turn it in. Once I write it down, I'm not going to accept it.
And yours is the most complete, so I trust that you know what you're doing. Well, are you going to tell us the trick after we turn it in? Is this just going to plug in?
But I want time, yeah, I want time today. That's the trick. But you want to see the outside, I'll go over it.
Oh, this, I need it goes to
Ready?
at S goes to 0. Put down the instant.
So go to S over S squared plus omega squared.
Is that what you look up?
Once everything evaluates out.
Are you going to go over that next class? No.
If you want to go over the analytic of it, then see me in my office hours, I'll do it. But that's Calc 2, so I don't want to spend time in this course doing Calc 2. Alright, so don't forget your homework journal. Final collection is the 14th, that's the day of the final. Final group assignment is due the 12th, which is coming up quickly. I just wrote that week's stuff for Blackboard. And start thinking about your green reference sheet for exam 3. Remember, the last exam I do have to make comprehensive.
So like cumulative? Okay.
And sadly, I don't have a choice, I have to make comprehensive. Well,
So is it
I
longer
don't
than
have to do anything, but I can be fired if I don't. So
is it longer than the ones we've taken so far? Okay.
it'll be 120 minutes, 2 hours.
Okay.
And it'll probably be 100 points instead of 60. But I won't know until I actually sit down and write it.
And is that next week?
No, exam 3 is August 15th.
Can we use all 3 reference sheets?
Just one. Just the one that I handed out.
Okay.
But you can use those two to maybe know. Oh, I forgot this on this exam, so let me write it on here.
Are we still gonna get a review sheet that's similar?
Yeah, that's going to be the day before. So on the 12th, we'll do the exam review, and the 14th will be the exam.
And that would be like a cumulative review?
I'm not sure what I'm going to do, if I'm just going to do the new stuff or not.
Okay.
I haven't decided. What's today, Tuesday? Thursday, we'll continue, we'll finish this up and then do inverse Laplace transforms. I'll see you then.
So what was the trick to not getting stuck in infinity?